In today's video, we're going to be talking about power. After watching this video, you should be able to determine how power and work are different from one another, and then be able to use the power formula to solve some problems. And we'll do a few example problems in this video to give you an idea of what I'm talking about. So let's get right to it. What is power? Okay, I mean, we all want it, right? But what actually is power in terms of physics? You may have noticed back in a couple of lessons ago that the formula for work, if you remember, was work equals force times distance times the cosine of theta. You'll notice that in this formula, time has nothing to do with doing work. Okay, the time is not part of the formula. And so I just kind of make this example of good employees versus bad employees. Let's say you have like a big old pile of bricks on your driveway and you want to move them to your backyard. And you're willing to, pay someone, I don't know, $50 to move these bricks to your backyard. If you have one worker who moves all the bricks back to your backyard, say in 2 hours, or you have another worker who moves all the bricks back to your backyard, say in 3 days, which is the better worker? Well, probably the one that does in 2 hours, right? Because you want to get started on your project using these bricks. The point is, actually, both of those people would have done the exact same amount of work. They would have both had put in the same amount of joules to move those bricks from your driveway to your backyard, even though one took 3 days to do it and the other one only took 2 hours to do it. Now, these are extreme examples, but the point is, the amount of work that was needed to accomplish that task would have been the same. Now, if we asked who exerted more power, or who had more power, the employee that took 2 hours to move the bricks or the employee that took 3 days to move the brick, well, clearly the one that only took 2 hours would have had more power. And the reason why is because now power looks at time. Time is in the equation. So it's work, which remember is in joules, divided by time, which is going to be measured in seconds. So it's joules per second. So the formula for power is work divided by time. Okay, so that's how power and work are different. Work is just solely looking at, how much force is needed to be applied to move something a certain distance. Whereas power uses the work formula, but now you add in a component of time. How long did it take to do that? And this kind of is, if you're into cars, I'm not super knowledgeable about cars, but if you're into cars, typically you're looking at a car like, well, how long does it take for it to go from 0 to 60? Well, that's referring to the power of the engine, right? I mean, if the engine's able to really get that car moving quickly, it has a lot more power than, say, I don't know, a Volvo, okay, where maybe it takes, 3 hours for it to get to 60 miles per hour. Not being funny, but point is, power is looking at work divided by time. Okay, so let's continue on. Power, the unit of power is the watt. Okay, so if you look at the top of your light bulbs, typically it's measured in watts, and that's a power rating. Okay, the higher the wattage the light bulb, the brighter it is. And 1 watt is 1 joule per second. Now, if you can remember way back when, I had a video lesson about ratio units. The watt is a ratio unit because it's joules per second. All right, and just for example, let's say I have a light bulb that's 20 watts. What is that actually saying if you have a light bulb that's 20 watts? Well, this ratio, basically you can start putting numbers in here where you just put a 1 on the bottom. In 1 second, this light bulb is going to use 20 joules of energy. And we'll talk more about this later, but it's a really good idea if you can start to understand what the units actually mean. That light bulb is using 20 joules of energy every second. That's what a watt is telling you, okay? Just so you know, so we can kind of talk about units that typically are used in our country, 1 horsepower is equivalent to about 750 watts. So if you have a 1 horsepower car, which isn't very powerful, your car would be using 750 joules of energy every second, okay? And then down here, this is just basically breaking power up into kind of a different look at formula, a different way to look at the formula. Power equals work divided by time. Now, if you remember, work is force times the displacement, and the cosine piece is left out here, but there is actually the times the cosine of theta, divided by time. Now, power also equals force times displacement over time, which if you think about what is displacement over time, well, that is velocity, right? That is velocity. And basically, you can also say power equals force times velocity. That's another way of looking at power. So it doesn't really matter. It'll all get you the same answer. But if you have different numbers in your problem or that type of thing, you can kind of look at things differently. Typically, when I think of power, I personally remember this equation. It just seems to work out that if you remember that, you're all good. But if not, you always can use these other forms of it. It's all the same thing. Let's do some example problems of calculating power, just to give you an idea of what I might expect of you. Okay. So it says, when doing chin-ups, a physics student lifts her 42-kilogram body a distance of 0.25 meters in 2 seconds. What is the power delivered by the student's biceps? All right. So a couple things. I'm going to kind of write down what I know. All right. So the mass of this student is 42 kilograms. And the distance or the displacement traveled by the student is 0.25 meters. And the time it takes for this student to move that far is 2 seconds. Okay. Now I cannot use my power equation, power equals work over time, right from the get-go. Okay. I just am not able to do that quite yet. What I can do, though, is I want to first figure out how much work did this student do to basically move a distance of 0.25 meters. And so if you remember, the formula for work equals force times distance times the cosine of theta. But in this case, the student's moving up and down vertically, and so the cosine of theta is just going to be 0, which would be 1. So I'm going to drop that out of the equation when I start filling in numbers. Now the force, do I know the force? Sometimes people want to put in the mass, and that is not the force. We need to calculate the force due to gravity. Okay, so F sub g is, if you remember, what is weight? Well, weight is mass times the acceleration due to gravity. That will give me the force in this problem. So I have to take 42 times 9.8 meters per second squared, and that gives me an answer of 411.6 newtons. Okay, that is the force of gravity on this individual as she's doing pull-ups. Is that it? Chin-ups. Sorry. Now I'm going to throw that into my equation. So this number is going to go right there. And now the distance, I know it's 0.25 meters. So I'm going to take this times 0.25 meters. And now the work that this student accomplishes, if you do this problem right here, 411.6 times 0.25, you would get 102.9 joules, okay, of work. So to do this chin-up, the student is going to expend 102.9 joules of work. Now, the formula for power is work divided by time. Okay, so now I know the work. It's this, 102.9 joules, divided by how long did it take her to do this? 2 seconds, right? So 102.9 divided by 2, if you do that problem, you would get a power of 51.5 watts, which the abbreviation for the watt is a W. 51.5 watts. So what is that actually saying? This student is expending 51.5 joules of energy every second to do these chin-ups. Okay, that's basically what this power rating is saying. All right, let's take a look at maybe a little bit more challenging problem right here. It says an escalator is used to move 20 passengers every minute from the first floor of a department store to the second floor. It is located 5.2 meters above the first floor. The average passenger's mass is 54.9 kilograms. Determine the power requirement of the escalator in order to move this number of passengers in that amount of time. Okay, let's first start off with writing down what we know. So the mass of one passenger is 54.9 kilograms. The distance is 5.2 meters. And the time is 1 minute. Okay, so that's great. Let's first start off with, let's change this mass into something that's more useful for us in terms of force, okay? So remember, the force of gravity equals m times g. So 54.9 is my mass, times the acceleration due to gravity, which is 9.8. And if I do that problem, I get a mass of 538.02 newtons. That is for one individual. Now this problem is telling us that 20 passengers are riding this elevator in a minute. So I'm going to multiply this by 20. So I figure out that just the total force on all the passengers. And if you multiply that by 20, we have a force of 10,760.4, that's 4, sorry, 0.4 newtons, okay? Now, remember, work is force times distance. Work is force times distance. And so if I calculate the amount of work done by the elevator, be work equals force times distance, and then again times the cosine of theta. But elevators typically just go straight up and down, so the cosine of 0 is 1. So I'm going to drop that out once I start plugging in numbers. So my force is 10,760.4 newtons times the distance, which they tell us in the problem is 5.2 meters. And if you do this math problem right here, I get a total work of 55,954.08 joules. Okay, that is my total amount of work. Now that is not what the question is asking for. They want to know how much power does this basically elevator use. And remember, power equals work divided by time. So I know the work, it's right there, this number right here, 55,954 joules, divided by the time. Now the one thing is, don't get yourself caught in this trick. Change the minutes to seconds. So 1 minute, there are 60 seconds in that. So I'm going to divide this number here divided by 60. And if you do 55,954.08 joules divided by 60, I get a power rating of 932.6 watts. At 932.6 watts. And again, what is that saying? Basically, this elevator is going to use 932 joules per second to basically accomplish this task. That's how much energy it's going to be using. Hopefully this helps you understand power a little better. That takes care of this video. I will see you guys next time.